Infrared spectrometry helps chemists to identify the functional groups present in a compound. They can therefore help in finding the structure of a compound. A pair of atoms joined by a covalent bond can be thought of as being like balls on the end of a vibrating spring. The bond can vibrate with different amounts of energy at a frequency that depends on the masses of the atoms and the strength of the bond. Lighter atoms give higher frequencies. Heavier atoms move more slowly and so give lower frequencies. Stronger bonds give higher frequencies, and weaker bonds, lower ones. At room temperature, most bonds will vibrate with the lowest possible amount of energy. But if radiation of the right frequency is supplied, the bond can absorb energy and vibrate with greater amplitude. Most bonds absorb energy in the infrared region of the electromagnetic spectrum, which corresponds to heat. Each bond, such as OH, C double bond O, NH, and so on, absorbs at a particular frequency, and this allows it to be identified. For historical reasons, and because the numbers are easy to work with, chemists dealing with IR spectra use units called wave numbers, measured in centimetres to the -1, which are proportional to frequency. All IR instruments have a source of IR radiation. This is a coil of wire surrounded by a ceramic capsule, which is heated electrically so that it gives out IR radiation. In other words, heat over a whole range of frequencies. The IR radiation goes via a series of mirrors into the sample, which is placed here in an appropriate holder. The radiation not absorbed by the sample arrives at a detector situated here. Modern instruments, such as this one, use a device called an interferometer, consisting of a beam splitter here and a pair of mirrors at right angles to one another. This produces what is called an interferogram from the source radiation. The interferogram holds information about the intensity of all infrared radiation at all frequencies simultaneously. This passes through the sample and to the detector. The interferogram that arrives at the detector can be decoded by a mathematical technique called a Fourier transformation. This gives the intensity of the infrared radiation at each frequency separately. The transformation is handled by the computer and produces a graph of percentage transmission against wave number. This is what the chemist interprets. The essential point is that pulses of infrared radiation consisting of a range of frequencies simultaneously are passed through the sample and arrive at the detector. Some frequencies are absorbed more than others, depending on what bonds are present in the sample. This is the sample holder. The sample is placed here on a crystal which is made of diamond or germanium. The IR beam is directed into the sample by a mirror. It is reflected back from the upper surface of the sample before being guided into the detector by a second mirror. This method is called attenuated total reflection, or ATR. Here, we will run the IR spectrum of solid benzoic acid. The instrument is switched on, and a blank is run with no sample in place. This is to find the absorption of the air, which must be subtracted from that of the sample. A little benzoic acid is placed on the ATR crystal. This is a holder for solid samples. Less than 1 milligram of solid sample is required. The torque wrench is used to squash the sample to ensure a good contact with the surface of the crystal. For most samples, no preparation is required. Details of the scan are entered into the computer. The spectrum of the sample is obtained within a few seconds. The wave numbers of the more significant peaks can be labelled onto the spectrum. This helps the chemist to interpret the data. This peak is caused by a stretching vibration of the C double bond O, and this by an OH stretch. These two peaks together suggest that the sample may have a carboxylic acid functional group, which has both C double bond O and OH bonds. An unknown sample may be identified by matching its IR spectrum with a database of spectra of known compounds, particularly in the region of the spectrum below about 1500 centimetres to the -1. The peaks in this area are due to complex vibrations of the whole molecule, and the area is referred to as the fingerprint region because it is unique for a particular compound. For a liquid sample, the procedure is the same, but a few drops of liquid are placed in this type of sample holder. The cover is to prevent the evaporation of volatile liquid samples.